All right, let's talk about another topic, kind of important topic under statistics, which is called as coefficient of variation. And if you see this tree, it's a relative measure of variability. So if you see here, it comes here on the green side, the far extreme right. So it's under the relative side of variability or relative measure of variability. And if you have not seen my previous episodes where I started from this point, please check it out so that it makes sense, because each of the absolute has a corresponding relative measure, and coefficient of variation or relative standard deviation, or even if it's called a coefficient of standard deviation by some textbooks, it's a relative measure which is related to this absolute measure of variance and standard deviation, which we pretty much covered in detail in the last two episodes. Variance and standard deviation are related, and hence we'll be just talking about only one relative measure, which is coefficient of variation. And even from an exam standpoint of view, that's what's covered. So let's talk about that. Okay. So let's first recap, because this whole measure is heavily dependent on standard deviations, on the concept of standard deviation, because variation and standard deviation are kind of related. So, and we have seen that standard deviation is nothing but a square root of variance or square root of sigma. So we need to understand what is the standard deviation. Let's do a quick recap. So standard deviation from the last two episodes, if you're focused on that, we know that it's pretty much a measure to give a sense of how far are we from the mean. So if this is kind of the mean line, and if the values are here, 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 and here, it tells on an average how far, what is the deviation, what is this distance of each of this value from the mean value. So it's dependent, it's relative to mean, it's directly dependent on the mean. That's what we know, standard deviation, or it's kind of often called as SD, and we know that. And this is the formula for the standard deviation, and we have seen, taking different examples, what is the standard deviation for ungrouped data and what is for grouped data. In terms of for group data, we just have the frequency. Otherwise, the formula is pretty much the same. Whatever you see under the square root, it's nothing but a variance, because you're squaring the units, and then you're taking the square root, which after that you get standard deviation. So that's what it is, whether it's called as S or SD. Okay, and we have seen this in the previous video. So now let's take a series of examples, and let's try to understand what is the primary need to have a coefficient of variation. Because in all the other videos we have seen that we have an absolute measure, like for example we saw in range, we saw over here range, and we knew that in certain cases range does not work, and then we kind of saw how we need to have a relative measure called as coefficient of range. Likewise, we have seen that in the previous videos. Similarly, let's try to understand what is the main issue that we have with standard deviation, because it's a very important measure, it's a great measure, but there are some problems, certain constraints in certain examples, and hence we have to not use standard deviation, but we need to have a coefficient of variation. But before directly jumping into that, let's try to derive that by taking few examples and getting a sense of it. Okay. So let's take the first example, and let me just erase this. Hold on. Get rid of this doodles to keep it clear. Okay. All right. So let's take a pizza delivery example. Okay. So now we have got two shops. Okay. One is the Pizza Hut and one is the Domino's. And these are the orders in terms of delivery minutes. So we have made 3 orders from each of these shops, restaurants, in 3 different instances, and we have got the delivery time in minutes over here. Okay, and the total delivery time in minutes is also the same, although the individual delivery varies, because it's 15 here, it's 18, it's 20 here, it's 19, it's 25 here, and it's 23. So the each order has been delivered at a different time by Pizza Hut and Domino's respectively, but the total delivery time for all the 3 orders is same, 60 minutes. And 60 divided by 3, if you take the average of 3 orders, it's 20, right? The 3 is the number of orders, order 1, 2, 3. So in this example, although the individual delivery time is different for both the restaurants, the mean time, the average time taken for all these 3 orders is still the same. So mean is equal to same, okay, for both the cases. So in this case, since the mean is same, how do we even judge, or how do you even conclude which restaurant is better in terms of the delivery time, overall delivery time? Obviously, we cannot use the mean, because if it was different, then we could have said whichever has a greater mean, that means they delay more. For example, if Pizza Hut had, let's say, 20 minutes of average delivery time and Domino's had, say, 30 minutes. So if mean were different for the same set of orders, then we could have concluded that Pizza Hut has a better delivery time. But in this case, the mean is still same for the both. So in such instances, how do we calculate which is a better restaurant in terms of the overall delivery time? And that's where the concept of standard deviation comes into play. And I kind of explained this in the previous videos also, when we saw why we need to move away from mean, and then we need to understand the standard deviation, stuff like that, right? So now, now how do we calculate this? I still want to know the answer to the question which restaurant is better in terms of delivery time. So now let's try to use this formula. I'm not going to solve this, but this formula is given here. Let's try to use this formula and try to calculate, and it's not a group frequency, it's ungrouped data, right? Simple data. So let's try to use this formula and let's try to calculate the standard deviation for both the restaurants, okay? So I just calculated it already, so you can calculate it offline, but the essence is to get the concept. So we have the delivery time here for each one of them, which is different. You see here, here, in here. This is same, the total sum of all the delivery minutes is same, and hence the average is same. But if you see the standard deviation, it's different here. And that's where the beauty comes. The standard deviation for Pizza Hut is 5, and the standard deviation for Domino's is 2.64. So let's pause for a minute and let's try to understand what does this mean in a contextual way, which I've already explained in the previous video, but let's go through this example. So what does it mean is, in terms of imply, not arithmetic mean, what does it imply when you have these two standard deviations regardless of the same arithmetic mean? Over here, if you see Pizza Hut, the standard deviation is 5 minutes because it's 5 here. So that means, this is like the English mean, that implies that usually the delivery is in 20 minutes, which is the average time, okay? And if there is a delay or a deviation, then it would be plus additional 5 minutes. And that's what the standard deviation implies. So the deviation from the regular time is plus 5 minutes. So whenever there is a delay with the standard deviation of 5 minutes, the total time is going to be 25 minutes because 20 minutes is the average mean and plus 5 minutes is the standard deviation. So it makes 25. So if there is a delay, at the most, the delay might be by 5 minutes and the delivery time will get pushed out to 25 minutes instead of 20 minutes. That's what this SD means. And in case of Domino's, what it means, the standard deviation is 2.64 minutes. It's roughly half the time. That means usually the delivery is going to be 20 minutes. So average is still the same. And if there is a delay by the Domino's guy, it's going to be at the most plus 2.64 minutes. So at the most, the total delivery time is going to be 22.64 minutes. And that's why if you see in the Domino's, they put the ad 30 minutes or less or the pizza is free kind of thing, right? You see the ad. And that kind of explains because they're very sure about what is their average time and what is the standard deviation. And they know that they can always beat this time of 30 minutes, including the standard deviation. And hence they promise that if they delay by more than 30 minutes or more, the pizza is on them, it's free kind of thing. So based on the standard deviation, we kind of conclude that Domino's overall is better in delivery times, and I personally like the taste too, than Pizza Hut. That's what it means. So based on just the average, it's very hard to conclude, but the standard deviation helped in this case. Whenever we have the same averages, the value of the mean, arithmetic mean is same, the standard deviation comes in play and it helps, which is actually better because it can help see through the details, and then we can calculate and we can identify or we can conclude which is a better play or where there is more variance or which is more consistent and so on and so forth. So in this case, we solve the example of pizza and we know that Domino's is better in terms of delivery time. Let's take another example now. Let's take the example of two students, student A and student B. In the first case, if you see, the mean was same. The average time was 2020, right? We saw that same. Let's take it here, okay? Now what we're going to do is, we're going to take two students, A and B. The marks are out of 70 and there are 4 subjects, okay? For student A, I've given the marks 55, 65, 45, 68. We have the total and then we have the arithmetic mean here, pretty much, which is 233, this mark divided by 4 subjects, and we have 58.25. But for student B, let's say he didn't appear for drawing because he didn't have to appear or whatever that is. He is just going to appear for 3 subjects, okay, and the total is going to be 65, and hence the average is going to be 165 by 3, and it's going to be 55. Okay, let's put it that way. Now how do we compare this in this case? And let's say I also calculate the standard deviation, which is in this case about 10 or so. One second, let me scroll it properly. Okay, over here. Okay, but can I make any meaningful conclusion based on this in terms of which student is better and which student is not better? Because it's very difficult, because it's not a fair comparison. For A, I've got 4 subjects, and for B, I've got only 3 subjects. So the base, it's 2 different data set. One data set has got 4 subjects, or n is equal to 4, and one data set 2 has got 3 subjects, n is equal to 3. And hence, if I calculate the mean, obviously the mean is not going to be the same unless the marks are adjusted, but the mean is not going to be same. And in this case, the mean is more for A. So does that mean that A has a better score than B? Actually not, right? Because the number of the data set itself is different. So in that case, even if you calculate the standard deviation, in this case, the standard deviation for A is actually more, 10.43. So it looks like B is more consistent. So it's all over the place, right? It's very hard to conclude. So in this case, we cannot just use a standard deviation to compare, because the data set itself is different in terms of the number of values. So the first observation that we make is when the averages are same and the number of order also is the same, the number of order is n is equal to 3. The n is same and the average is same. In those cases, SD comes handy, and it really helps us, which is better, which is consistent, where there is less variance and stuff like that. But in cases where it's a different data set, where we are comparing the number of observations are not the same, over here it's 4 and over here it's 3, regardless of how the averages pan out, if the average could be more, it could be less, it could be same, but we still cannot use the SD, standard deviation, for comparison, because these are 2 different data sets with 2 different number of values. That's the first observation where SD will not work. Okay, let's take another example. Let's try to compare 2 different examples which are not even related. For example, let's take the 2 examples that we saw above, where in the first example we have the pizza delivery example, delivery in minutes of Pizza Hut. In the second example, we have the marks. So in essence, we are comparing delivery time versus marks. Like it's all as good as comparing apples and oranges, because both are different fruits and not comparable. So in this case, although we have the average over here, we have the SD over here. Can we even compare? Again, we cannot compare, because these are 2 different sets of data with 2 different units. The unit of measurement over here is time, and over here is marks. So again, the SD will not work, because we cannot measure 2 data sets which are expressed in 2 different units of measurement. So that means we have got the second observation where the SD does not work. So what is the solution? In this case, I still want to compare in terms of which of this data set is more consistent, either in this case where the students have got different subjects, or in this case where I'm comparing 2 different things. I just want to measure agnostically, without worrying about what is the underlying unit of measurement and everything, which data set is more consistent and which data set is more varying, has more variance. I just want to measure that. So how do I do that if I cannot do by standard deviation? What is the way to do that? The answer to the question is, in such situations, we use something called as coefficient of variation, or CV, which is called as CV. Okay, and CV will always help, regardless of you have different units of measurement, or you are comparing 2 different data sets with 2 different values. It does not really matter. CV will eliminate those things, those kind of nuances, and still give us a value. The only thing is, it will not give a value in any unit of measurement. It will be giving the value in terms of a percentage, like how we express the percentage. Instead of comparing the marks, if you say the student A has more percentage than B, it's easier to understand, something of like that. And since coefficient of variation, if you see the top hierarchy, that hierarchical tree, it's a relative measure. That means it's a ratio. It's a ratio of 2 numbers. Okay, and what is it? What is the ratio of 2 numbers over here? What are the 2 numbers we're talking about? It's a ratio of standard deviation over mean. That means you take the standard deviation, you divide it by mean, and you get this ratio. And since you want to express it in terms of percentage, you multiply by 100. So CV is a relative measure. It's a ratio of two numbers. It does not have any units of measurement. It's expressed as a percentage. And the formula is, if over here, if you see the statistical formula, it's standard deviation expressed by sigma divided by the mean. Either you can say x bar or you can say mu, does not matter, into 100. And it's expressed in percentage. And as a clue, you can remember this way, right? If you want to remember this formula, S for standard deviation divided by mean into 100. Doesn't matter how you remember, okay? So that's what is CV all about. And pretty much what it is, it's a statistical measure of the dispersion of the data points in a particular series, that means in a particular data set. And it's centered around the mean value. When I say centered around the mean value, let me correct it. Not centered, it's with respect to the mean value. It's in relation, in relative to the mean value, what is a CV. So that's the reason the mean comes in the denominator. It's with respect to the mean value. And since the ratio, the units gets cancelled. For example, if you're talking about marks, the SD is given in marks over here. And even the mean in the denominator is expressed in marks. And since the units cancel out each other, it does not have a unit of measurement. It just is a percentage. So just remember that. In that case, it really helps us to eliminate the nuances of what SD cannot resolve. And then we can get a fair comparison. Doesn't matter what data sets you compare and how are they organized. And let's see an example of that. And before we go into the example, the most important thing, I'm going to just make it 3 asterisks here or 4 asterisks, is the way you need to think about the CV is it's an inverse measure. What does that mean? The lower value, the better the consistency. So we should desire to have a lower value of CV, not a higher value. The variation should be less. So lower value of coefficient of variation is preferable because it expresses lesser degree of volatility. That means lower the CV, better is the option. Smaller the CV, higher is the consistency. So all are different words. Basically, the bottom line is CV should always be lower. That's the desired outcome because it kind of expresses the ratio. So the lesser it is, the better it is. It's more stable, less variance, and more consistent. And in the exam, you'll always have problems asking you to, they'll give you 2 data sets and they'll ask you to say which one is more consistent. That means you have to find the CV, that's your clue. And whichever has a smaller value, that means it's less variant or it's less varying to that degree and hence more consistent. So the smaller the CV, the better the consistency. And let's take an example, the last example, where we can see how should we measure this. Now, and this kind of an problem in the examination that has come, real-time problem, I'll solve in the next episode also, but this is the exam problem, so we can focus on this. So let's take the runs of 2 batsmen. It's a very easy example in terms of cricket. So we have got 2 batsmen, batsman A and batsman B. And they play 5 one-day matches. So number of matches they play is still the same. So N is equal to 5. Observation is equal to 5. That's the same. But the score, the average is different. One guy scores 44, one guy scores 54. And we don't have the individual score for each of the matches. We just have the consolidated. Based on this, we have to find out, because if we had the individual, we can see the number pattern and see which is more clustered or which is more closer. For example, if it's 44, 43, 42, like that, we know that this is more consistent, whereas one is 45, one is 39, and so forth. So we can calculate that, but this is not there with us. So based on the average score and the standard deviation, we'll have to find out which batsman is more consistent. So in these cases, the CV really comes handy, because if you see here, it's a very interesting problem. If you just take the average score, okay, one guy is scoring 44, one guy is scoring 54. That means in that case, just based on the score, we can say B is better than A, because B's average score is more, so he's getting better score. But if you take the standard deviation is like how far it is from the mean. In this case, standard deviation for A is less. So standard deviation for A is less than standard deviation for B. That means there's less deviation for A from the mean. Does that mean that A is better than B? So it's a confusion, right? Because it's very hard to figure out from this who is better than whom in terms of the consistency, which batsman is more consistent. So in such cases, we will use coefficient of variation or CV, because if you see, that's what I'm putting it here. B has got more average. Does that mean that B is more consistent? Is it true? I don't know. And if you take the SD of A is less, does that mean A is more consistent because the variation is less or the deviation is less? Even I don't know. What is the correct answer? The correct answer is to find the CV. And this is one of the examples where even if you have different means, it's for the same set of matches, it might be tricky to find the consistency, and hence we go with the coefficient of variance. And what we do here is we take the same table. So this is given to us, okay, and I calculate over here. It's a simple formula. It's a ratio of two numbers. I'm going to take the SD over the mean. So this will be in the numerator and this will be in the denominator. I'm going to multiply by 100. Okay, so if you see the value here, the batsman A, the CV value for batsman A is 11.59, and the CV value for batsman B is 11.68. That means the CV value of A is less than CV value of B, and I have told the lesser value, the better the consistency, or higher the consistency. If you see my last red bullet, smaller the value, higher the consistency. That means since the value of A is less than B, I can safely conclude that A is more consistent than B, and that's your answer. So if you can see that what appeared to be consistency is completely different when you calculate the CV, and hence CV in terms of certain examples where SD cannot work, CV is a great way to calculate the consistency or a measure of variance or variation. And that's how we calculate the C, and this is the final answer. So the final answer in exam, if they ask you a question, which they definitely ask, it's an easy question. Just calculate the ratio SD over mean, multiply by 100. Whichever is less value, that particular value is more consistent with respect to the other. That's how you calculate. So my closing comments on coefficient of variation. It's a relative measure, no units of measurement. It's expressed as percentage. It's a ratio of standard deviation over mean, and this is the formula. This is standard deviation sigma over x bar into 100, and that's how you calculate the CV in terms of percentage. And a quick side note, in some textbooks, they also cover a term called as coefficient of standard deviation, not variation. And pretty much it's the same. The only thing is it's not multiplied by 100. If you see this, they just leave it as a ratio. They don't multiply it by 100 because it's not expressed in terms of percentage. It's just a ratio. But normally you'll not find any examples in exam asking for standard deviation because that's not very common. But if they ask, you know that you should not be this thing. So you can just write both of them. If you want a coefficient of variation, CV, you express in terms of percentage with the same ratio. And if you just want to find coefficient of standard deviation, just the ratio without multiplying by the 100 and no percentage, it's just going to be a number in decimals or something like that. And in terms of extra reading, these are the two websites I referred, which gave a lot of clarity on how to think about that and a lot of inspiration drawn. So credit to these two websites. And hopefully the concept is very clear on what is CV now. And with that, we pretty much conclude the super focused syllabus specific topics under statistics from an examination standpoint of view. And in the next few episodes, I'll be solving some of the problems related to variance, standard deviation, and coefficient of variation. Since all of these are related, I thought let me cover all these three topics together and solve them at once. I'll see you in the next episode. Hopefully this was very clear.